For my Choose Your Own lab, I chose to do some archery physics. In this lab, I recorded the trajectory of an arrow fired from a traditional bow. I have 3 questions I'm trying to answer by analyzing the video. Can I determine the strength rating of the bow? Can I build a model to match the flight of the arrow? And can I use the model to predict which angle will fire an arrow the farthest? The main physics concepts we're using in this lab are Newton's second law and the energy principle. Newton's second law is going to be used to calculate and predict the motion of our arrow. And then we can use the momentum principle and the energy principle to check our work and make sure that we've done everything correctly. Part 1. Analyzing the video. I placed the axis with the origin at my feet and align the horizontal axis using the point of impact of the arrow in the video. The positive x direction is to the right, so my shot is in the negative x direction. I have the initial position and the mass of the arrow was 0.083 kilograms. Now using only the tracker data, we can find the following: the shot angle, the arrow acceleration, the magnitude of the force of the shot, which is the bow strength, and also the vector force of the shot. I calculated the shot angle using my first and third positions and some trigonometry. I found that the tangent of the angle was equal to the change in y over the change in x positions, and that angle was 7.7 degrees. To find the arrow's acceleration, I used the first and second points from my tracker video. I knew the impulse was applied over just one video frame, so that time was 0.033 seconds. And in that time, the magnitude of the change in the distance was 0.44 meters. That gave me an average velocity of 13.2 meters per second. But since I know that the initial velocity is 0, I found my final velocity was 26.4 meters per second. And using that, I can find the acceleration by using the final velocity is equal to the initial velocity plus the acceleration times the time, which is a version of Newton's second law. And I found my acceleration to be 792 meters per second squared. To calculate the magnitude of the force of the shot, I'm going to use Newton's second law as the momentum principle. I've got my initial and final momentums here calculated with the mass times the velocity. So the change in momentum is equal to 2.19 kilogram meters per second. This gives me a magnitude of my force of 65.7 newtons. I can check that using the traditional F equals ma, and again you can see I get 65.7 newtons. Now I can check using the energy principle as well, where my work is equal to the force times the change in distance, and I know that that is equal to the change in energy. My work is calculated here using the force times the distance, and that gives me 28.9 joules. I can check the kinetic energy of my arrow moving at a velocity of 26.4 meters per second squared, and we can see I also get 28.9 joules. So far everything works out. To get the vector force of our shot at any given angle, we're going to do a little trigonometry and use the magnitude of the force as the hypotenuse of a right triangle. We break the force into its x and y components by doing this, and you can see the value here. Part 2. Building the model. First I have to set up my initial conditions, and you can see those over here. Then I need 2 separate while loops, one for the force impulse and one for the flight of the arrow. Our first while loop is the impulse, and we know that the force is applied for only one frame. We then can use our vector force that we calculated earlier and add it to the weight force to get the net force on the arrow. We can then use Newton's second law to predict the velocity as it travels through the air and then also calculate the positions. Our second while loop is the flight of the arrow for the remainder of the time. We have the weight force, but we also added the drag force now to the flight, and we add those together to get the net force. Again, we use Newton's second law to predict the velocities and the position of the arrow. I used turbulent drag in my experiment, and we can see the assignment statement here, where b is the drag coefficient, and this part at the end is really just negative v hat, which gives my drag force the opposite direction as the velocity. To find the drag coefficient, I used the initial and final positions from my observations, then I edited the value of the coefficient until my model's x position matched that of my observations. And with that, I got a drag coefficient of 0.00357. When we run the model and then compare the data, we see that the model reaches a higher y position and would also go farther in the x direction. Now, why don't these original plots match? A real arrow is not a point mass. The arrow I used was pretty long and had a heavy tip, which would drastically alter its flight characteristics. Also, improper measurements or warping due to the camera lens, and perhaps the force is applied for less than one video frame. I decided that I should change the impulse to see what would happen if I changed the model so that the force is applied over less time. I applied the same 65.7 Newton force over a period of only 0.026 seconds, and we can see the results here. The model now reaches a similar height and distance, And this leads me to believe that the bow applies its force over a time period faster than a standard camera is able to capture. So I plugged in various angles in order to find the angle that would give a shot its maximum range. This was determined by finding the point where y equals 0, meaning the arrow had struck the ground. I used trigonometry to break the force into the force vectors for the desired angles. And here's the ranges that I got, and we can see that 40 degrees is the longest. To try to apply this to the real world, I went out and I shot an arrow at 40 degrees with a force of 57 newtons. My model said that this arrow should travel 24.1 meters before it hit the ground. My shot, in actuality, went 24.9 meters, which puts my estimate at a 97% accuracy. It's not perfect, but it's pretty good for a simple model and some basic video analysis. So let's revisit the questions and see what we found out. The strength rating on my bow was 14.77 pounds. I gathered data from observations and used that to discover the acceleration and use Newton's second law to calculate the force of the shot. I was able to check my work using the energy principle. Could I build a model? Well, my model was able to match observations and accurately predict some future outcomes. And I used that model to find that a 40-degree angle would fire an arrow the farthest, and at 65.7 newtons, at a 40-degree angle, that arrow is going to travel about 26.7 meters before it hits the ground.